Okay, now for the proofs in 4.2b. The proofs are going to start to get a little bit longer because we have more theorems to deal with. The idea of working a proof backward is also very important. Because we have so much information, it always helps if you have the right information on the right proof, we have so much information that is given to us. We have to know and be able to eliminate what information we need. So I'm going to look at my prove line first. I'm being asked to prove something is a parallelogram. That means I need, by definition, pairs of parallel lines. The only way I know how to prove lines are parallel is to find those angle pairs, alternate interior, alternate exterior, corresponding, and same side supplementary. Since I know I'm looking for angles to say lines are parallel, which will let me say parallelogram, I now have a plan to what I'm doing. So mark my picture. 3 is supplementary to 2. Can't do anything for that right now. And 3 and b are equal. So let's get our given up here. Angle 3 supplementary to angle 2, angle b equals angle 3. Given. Now, the first thing I'm going to deal with are those angles. And since I want to ultimately prove the lines parallel, when I look at that given and I extend my pairs of lines that might be parallel, I can see that angle 3 and angle B are actually alternate interior angles. And since they're equal, that means my lines are parallel. So AD is parallel to BC because alternate interior angles imply parallel lines. So now I have one set of my lines parallel. Now I have to figure out how to get the green ones parallel. I've given a hint because all of my numbered angles are over here along this blue transversal. So let's use the supplementary given information. I know that whenever I have words, I always want to change it into an equation. And that is by the definition. Now, when I look at my picture, 3 and 2 aren't any of my parallel line pairs. But if I could link 3 with 1, they are corresponding. Then I could say my lines are parallel. Or if I could link 4 with 2, they are corresponding, and I could say my lines are parallel. I see that angle 1 and angle 2 make a linear pair. So I'm going to use that because that gets that angle 1 into my problem. You could have done the same thing with 3 and 4 to the same reason. Now this brings up an old pattern that we like to see. If you remember back to Unit 1, one of the first ways we started to do proofs is if two sums were equal to the same thing, those sums were equal to each other by substitution. This is also something that we liked to see because if I'm adding the same thing to both sides, I can subtract it, and now I have that angle 1 and angle 3 are equal, and 1 and 3 are corresponding angles. And so I can say that AB is parallel to DC because corresponding implies parallel. And now that I have parallel lines here and parallel lines here, I can say that ABCD is a parallelogram. And I say that by definition, parallelogram. And just like I did with the proofs with triangles, I can make myself a little note, not required but nice, by steps 2 and steps 7. So then I know exactly where my information came from that allowed me to say that they are parallel. Now this proof is going to start with even more given information. I'm going to be given that that figure is a rectangle. So that means I have the 6 properties of a parallelogram plus the 2 more additional rectangle properties at my disposal. All right, so being as I have so much to choose from, I really have to work this one backwards. What I need to try to prove is that this triangle right here is isosceles. Now, in order to say that a triangle is isosceles, I have to say that there are 2 equal sides. In this picture, EC and EB seem like the most likely candidates to be my equal sides. Well, what are EC and EB? They're parts of the diagonals of the rectangle. So now I know which of my theorems I need to use because I'm only going to focus on the diagonals. I don't care about the opposite sides, the opposite angles, right angles. I don't care about any of that. I just need the theorems and the properties that tell me about the diagonals. So let's get started. This is really where you're going to start to see all of the information from the first 3 units coming together and being used in one proof. So the first thing I'm going to do is I'm going to say that DB is equal to AC. And the fact that the diagonals are equal is a property of a rectangle. Now, I've got my big diagonals in place, but I don't have those pieces entered into evidence, entered into my proof. And we know that we always need to try to get our pieces that we're going to need on our paper in our list. So I have an old theorem from Unit 1 that I really like, and it was called that parts to whole. I know that DB is equal to its parts, DE plus EB, and I know that AC is equal to its parts, which is AE plus EC. Now I like that because it gets my pieces that are part of that isosceles triangle on the page. That EC and EB that I'm eventually going to try to get equal, it gets them on the page. So again, one of my favorite theorems is if I have things that are equal, that then are also equal to sums, I can set those sums equal to each other. And that's by substitution. Now typically, when we get to this substitution part, we can either make another substitution and subtract a way to get our desired pieces by themselves, or we have that subtraction step. But I don't know that DE and AE are equal. So I have to go looking for that. And one of the properties of a parallelogram is that the diagonals bisect each other. So I know that DE is equal to EB, and I know that AE is equal to EC. And that is a property of a parallelogram. Now the reason this helps me is I can take these two and I can do a substitution into here. And that substitution is going to look like this. EB plus EB is equal to EC plus EC. So what I did was I replaced this one and this one based on these. Why did I do that? Because remember, my goal is to get EC equal to EB. I'm going to do a little algebra. EB plus EB is 2EB. EC plus EC is equal to 2EC. That's addition. I'm going to divide by 2. And I have what I want. If those two guys are equal, then triangle CEB is isosceles. And that is the definition of isosceles. These proofs are longer, but if you look at this one, for example, there are only 2 new pieces of information in it. The rest is all old information being put together with a new picture. So give them a try, give them a good effort, and you might surprise yourself. Good luck.